This is the solution to question 4 on homework 4. We're asked to imagine two objects sliding down a slope. They've got different coefficients of friction, so left on their own, this one would accelerate faster because it has less friction. That one would accelerate slower because it has more friction. But they're cabled together, so this means that the extra friction from the top one will try to slow it down, meaning the cable must speed the top one up. Likewise, this one has less friction, so it wants to go faster, but the cable will slow it down. The force diagrams for both of them are almost identical. This is the second time I'm recording this, so I've already got them drawn. The normal forces are normal to, perpendicular to the surface. Friction arrests the motion of both of them, pointing back upwards. And I've decomposed gravity into components parallel to and perpendicular to the slope. The only difference is tension. Tension pulls the top one down and the bottom one up. So now let's construct Newton's laws. I'm going to do the perpendicular directions first. So the only things I have here are normal forces and gravity. Fn1, Fn2, minus m1g cosine theta, minus m2g cosine theta. Now, we know the accelerations in the perpendicular direction are 0. But I'm going to go ahead and get all the equations written down and then put that in. In the parallel directions, in both cases, gravity pulls them down the slope. So m1g sine theta, m2g sine theta. Friction pulls them back up the slope. And I know the formula for the force of friction is the coefficient of friction, mu, times the normal force. So I'm going to go ahead and put that in. Let's see, friction goes up the slope, which I've decided is negative, so mu1 Fn1, mu2 Fn2. Tension is the one that's different. In the case of the top one, it pulls it down, so plus T, and in the bottom one, pulls it up, minus T. This is equal to M1, A1 parallel, M2, A2 parallel. All right. So now I'm going to do some things with my eraser. The first thing I observe is that the accelerations perpendicular to the slope are 0. That's real convenient. Now, I also see a relationship between m1 and m2 and mu1 and mu2. I'm going to put this down in this corner. So, note, I'm going to call m1 equals m, m2 equals 2m. So now let me make that substitution again with my eraser. That's just m, that's 2m. This is m, that's 2m. And likewise, we'll do the same thing over here. I also noticed that these parallel accelerations are the same. They're cabled together after all. So I'm just going to call that A. Finally, I noticed there's a similarity with mu's, except this time, mu2 is the big one and mu1 is the small one. So I'm going to say mu2 is mu, mu1 is 2 mu. Let's do that again with our trusty eraser. That one's mu. This one's 2 mu. Now here's an algebra trick that I learned embarrassingly late in my education. I could solve this equation for A, substitute it in here, and then solve for t. Problem is, if I solve for a, I'm going to divide by m, and then I'd multiply by m. And I'd spend a lot of time just dividing and multiplying by something over and over again. So I can just take all of this stuff that equals ma and substitute it in for the expression ma. Now, we've got this 2 out front, so I need to multiply all these things by 2 when I do that. So I'm going to take the bottom equation and I'm going to equate it to 2 times that. So I've got 2mg sine theta, where's my blue chalk, minus mu fn2 minus t, and now I'm going to put a 2 in front of all these terms. So this gives me 2 mg sine theta minus 2 times another 2 mu fn1, and then plus 2t. This looks a little messy, but I can already start canceling things. This cancels with this. Notice here the 2 came from the fact that the mass of the bottom one is 2m, but this 2 came from the right-hand side when we did our substitution. That's okay. Now, I can just solve for tension. So I'm going to put all the t's over here, and I'm going to put all the other stuff over on the left-hand side. Let's see, so I've got, this comes over here and becomes positive. 2 times 2 is 4. So I have 4 mu fn1 minus mu fn2 equals 3t. What now? Well, I can find out the normal forces pretty easily. Up here, fn1 is mg cosine theta, fn2 is 2mg cosine theta. So now let's put that in. So I have 4 mu times mg cosine theta minus mu, normal force 2 is 2mg cosine theta. All that equals 3t. So, hey, I can just combine these, right? So this gives me 2 mu mg cosine theta equals 3t. So t is 2/3 mu mg cosine theta. So let's type that into Google Calculator real quick. You won't see me type, but I just want to figure out what number that is. So I have 2/3 times 0.1 times 1 kilogram times 10 meters per second squared times the cosine of 30 degrees which gives me 0.577 newtons. So that's the solution to question 4. This was more complicated than what we've done before, right? But ultimately the process is the same. Construct your force diagrams, construct Newton's laws from them, and then do some algebra to solve for what you want. One of the things I'll note is, I actually did this a couple of times on the board and ran out of space because I took a path through the algebra that was more complicated than it needed to be. over time, with some experience, you will learn ways that make the algebra simpler. You just kind of get experience finding the quickest path through the algebra. But if you did something else, that's totally fine. There are many paths through the algebra. This one just happens to be the quickest, which I demonstrated here because it got us to a final answer in one chalkboard worth.